Hi folks, we are going to start Module 6 and we're going to start with kind of a middle school review. So hopefully the QOD that you worked on, it will kind of refresh your memory of things that you already know, and if not, then this video will. And if that still doesn't help, then you can check your textbook, and I'll show you at the end of this video how to access your e-textbook to look through Chapter 2, which is where this material is covered. So, Module 6 is all about matter and energy. And so first we need to talk about matter and what it is. Really, the learning objectives from today aren't truly for this module. They are, as I said already, repeats from middle school. So, what is matter? Before we can talk about what matter is, we need to have a couple definitions. First, we need to define mass. Mass is a measure of the amount of matter that an object contains. The SI base unit of mass is the kilogram, as we learned last module. And volume is a measure of the space occupied by a sample of matter. So it's the amount of space that something takes up. Matter is anything that has mass and takes up space. So it has both mass and volume. So what are the building blocks of matter? The fundamental building blocks are atoms and molecules. What are they? An atom is the smallest unit of an element that still maintains the properties of that element. Can you break an atom up into smaller parts? Yes, you can. You can break it into protons, neutrons, electrons. But those individual particles don't have the same properties as the element. So you need to retain the properties of that element. An element is a pure substance made up of only one kind of atom. And we'll look more in that next topic, but it needs one kind of atom always needs to have the same number of protons. A compound is a pure substance made from the atoms of two or more different elements chemically bonded together. When these three words come up, typically there's a fourth word that comes up, which is molecule. Molecule is a little more complicated. People often define it as being the smallest unit of a compound that maintains the properties of that compound. That's not always true. A molecule doesn't have to be from a compound. It can be, like a molecule of carbon dioxide. So this carbon dioxide molecule is the smallest particle of the compound that still has the properties of carbon dioxide. But a molecule could also be an element, like oxygen gas is two oxygen atoms double bonded together. Here we only have one element, one type of atom in this molecule. So this is an element even though it's a molecule. So you can have element molecules and you can have compound molecules. So just to kind of clue you in that can be a little bit tricky. All right. So how do we classify matter? There are many different ways to classify matter. Here are some of them. All matter can be separated into two categories: mixtures versus pure substances. A mixture is a blend of two or more types of matter. It's important to realize that in a mixture, each part of the mixture retains its own identity and its own properties. So if you have salt water, the salt still retains its own salt properties and the water still retains its water properties. Each retains its own identity. The salt molecules and the water molecules don't chemically bond together. With mixtures, there are two different types of mixtures. You can have a homogeneous mixture, which is uniform in composition, and we call these solutions. Now, when we talk about solutions, most people think about some sort of solid dissolved in water. But a solution can mean more than just that. Air can be considered a solution. You can have a solution in gas. You can also have a solution in solid form. So when you're making an alloy like stainless steel, that is considered a solution because it is totally homogeneous, completely uniform in composition. But most frequently, when we say solution, we will be talking about some sort of solid dissolved in water or other liquid. A heterogeneous solution, a heterogeneous mixture is not uniform throughout. So if you take a sample from here and a sample from here, they might not be identical. One example of that would be a salad. If you've got lettuce and tomatoes and cheese and whatever in your salad, it's a mixture. It's not uniform throughout. If you stab your fork over here, you might get a piece of lettuce. If you stab your fork over here, you might get a tomato. On the other hand, contrasting with mixtures, you can also have pure substances. A pure substance has a fixed composition, and they are different from mixtures because every sample of a pure substance always has the exact same composition. Therefore, every sample of a pure substance has the exact same characteristics. So this is even if you get down to the one molecule or one atom level. If you pick out one atom here and one atom here, they're exactly the same. And you can't achieve that even with salt water. If you pick up one molecule and one molecule, they won't necessarily be the same. Here you might get a molecule of water, and here you might get a molecule of, well, you don't have molecules of salt because it's ionic, but you get my point. So every sample of a pure substance has the exact same composition. There are two types of pure substances, and we've mentioned these already. First, compounds are made up of more than one type of atom chemically bonded together. Therefore, compounds can be decomposed. They can be broken down into more simple compounds or elements through a chemical change. Elements, on the other hand, cannot, because remember, they're only made up of one type of atom. So here we've got gold, Au, is on the periodic table. It is an element. Here we've got mercury, Hg. It's on the periodic table. It is an element. Here we have water. Water is H2O. We've got oxygen and we've got hydrogen, two or more different kinds of atoms chemically bonded together. It is a compound. Here we have sodium chloride, table salt. Sodium and chlorine, two different types of atoms chemically bonded together, makes a compound. Here we have chlorine gas. Chlorine gas is a molecule. You have chlorine bonded to chlorine, but it is just one kind of atom. So we still call it an element because there's just kind of one kind of atom in that molecule. And here we've got copper, again, an element from the periodic table. Physical properties versus chemical properties. A physical property is a characteristic that can be observed or measured without changing the identity of the substance. For instance, boiling point. The boiling point of water is a physical property. P-O-I-N-T. The boiling point, malleability, your ability to take a metal and hammer it into a sheet, is also a physical property. It doesn't depend on changing the substance. When you boil water, it goes from a liquid to a gas, but it's still water molecules that you have there. You haven't chemically changed the water. With malleability, you started out with a solid lump of copper and then you hammered it into a sheet. It's still copper. It has not changed its identity. Contrast that with chemical properties, which relate to a substance's ability to undergo changes that transform it into different substances. So here you might talk about flammability. How easy is it for something to, a particular substance to catch fire? Another chemical property would be like ability to rust. So for instance, if you're comparing stainless steel to iron, stainless steel is less likely to rust than iron is and that is a chemical property of stainless steel. So, again, talking about physical and chemical characteristics, now let's talk about physical changes versus chemical changes. So, a physical change is a change that does not involve an actual change in the identity of a substance. So some examples of these would be things like cutting. If I take a piece of paper and cut it into small pieces, that's a physical change. I still have paper. I have not changed the identity of the material. Therefore, it's not a chemical change, it's a physical change. Another example would be boiling. As I said on the previous slide, when you boil something, when you boil water, you're going from a liquid to a gas, but you still have water molecules. You haven't changed the identity of those particles. However, if you change one or more substances to convert them into different substances, then that is a chemical change or a chemical reaction. So some examples of this, the most obvious example is burning. When you burn something that like burning a piece of paper, you are taking the molecules that are in the paper and converting them to carbon dioxide and water. So you are changing the identity of those molecules. Whenever you cook something, you are changing the proteins and changing them into different configurations and breaking them apart chemically. So those are two examples of, we'll go ahead and put down rusting as well, since I mentioned that earlier as a chemical change. So with these chemical changes, with these chemical reactions, how do we show them? So let's talk about burning coal. We already said that burning was a chemical reaction. So we've got carbon, and when you burn a substance, that's a reaction with oxygen. And in this case, our product is going to be carbon dioxide. So we have carbon plus oxygen. Carbon is reacting with oxygen to form carbon dioxide. That's a little bit shorter than my first sentence, but chemists like to go one step further and really abbreviate that down. We use the chemical symbols from the periodic table. Carbon is C. Oxygen, gas, is actually two oxygen atoms chemically bonded together. And then carbon dioxide has the formula CO2. And we'll look at naming these molecules and substances later. But for right now, what I want you to see is that in a chemical change, when we show a chemical reaction, we have reactants to the left of the arrow and products to the right of the arrow. So what are the signs that a chemical change is happening? How do you know that a chemical change is happening? There are some different signs. A lot of times students say heat is a sign of a chemical change or a temperature change. But the thing is, because some chemical reactions actually get colder, not hotter, but there are some physical changes that also cause a temperature change. So that's not a reliable sign of a chemical change. The ones I'm going to tell you here are more reliable. So one sign is the production of a gas. If you see bubbles coming out of a reaction mixture, then that's a good sign that there's a chemical change happening. Now, the one caveat to this is that the production of the gas cannot be due to a phase change. So if you're boiling water, you see bubbles. But that bubble production is due to the water going through a phase change, going from a liquid to a gas, and so those bubbles are produced. So it's important to remember, make sure that you're not, that the production of the gas is not due to a phase change. Another sign of a chemical change is the production of a precipitate. A precipitate is a solid that appears from a solution. So if I've got a solution and I mix them together, and then all of a sudden my liquid mixture looks cloudy, that's because there are teeny tiny particles of solid actually in my solution that weren't there before, and that solid makes the solution appear cloudy. Again, if you see a solid appearing, you need to make sure that it's not due to a phase change. So if I put water in the freezer, a solid will appear. That's not the kind of solid that I'm talking about. I'm talking about a solid that appears from something other than a phase change. So again, you have to just watch to make sure that you don't have a phase change. If light is produced, then you have a chemical reaction. If there is a change in odor, then that is a sign of a chemical reaction. If you have a change in color, that is also a sign of a change in a chemical change, a chemical reaction. However, you need to make sure that you don't just have an average of colors. So sometimes students kind of take a pink substance and add it to a glass of water, and then the glass of water magically appears light pink. That is not a sign of a chemical change. That's just an averaging of the colors. Like if you take a drop of like red food dye and add it to your glass of water will be pale red or pink. If you take a red substance and a blue substance and mix them together and you get purple, that's an averaging of the colors. However, if you add two clear substances together and suddenly a color appears, that is a true color change because you're not just kind of averaging the colors of the liquids that you have. Okay, let's do some of these. Are these examples of physical changes or chemical changes? Pause the video, have a go, come back and check your answers. Cutting paper is a physical change. Iron rusting is a chemical change. Water boiling, we've already mentioned this one before, is a physical change. Molding silly putty is a physical change. Cooking an egg is a chemical change. Breathing in and out, the breathing process itself is a physical change. You're just moving the air from out here into your body and then back out again. Although what your body is doing is a chemical change. The chemical reactions in your body that are taking oxygen and releasing carbon dioxide. Condensation on the outside of the glass, that is a physical change. It's kind of the opposite of vaporization. Instead of going from liquid to gas, we're going from gas to liquid. So, I already told you that it's a physical change when you convert between the different states of matter. But we need to talk about those states of matter to make sure that we know what they are, because that's another way that you can categorize, classify matter. So there are four main states of matter, three really that we'll be talking about this year. A solid has a definite volume and a definite shape. A liquid has a definite volume, but not a definite shape. It takes the shape of its container. Gas does not have a definite volume, and it does not have a definite shape. So it takes the shape of its container, and it will expand to fit any container that you give it. So any container you give it, it will expand to fit that container. Plasma has an indefinite volume and an indefinite shape. It's less dense than a solid or liquid, so it's more like a gas in that sense. It's the most abundant state of matter in the universe because it's what stars are made of. But it's made up of ions and free-moving electrons. But we're not going to be dealing with plasmas in chemistry class this year. So, how do we talk about solids and liquids and gases? How can we model the differences between solids, liquids, and gases? We do that using what are called particle spacing diagrams. It shows how particles are organized and arranged, and also gives an indication of their speed in different types of substances, solids, liquids, and gases. So here's an example of, this is a diatomic gas like oxygen molecules, two oxygen atoms bonded together. So here might be an example of the gas form. Gas particles are extremely fast moving. So we draw kind of big arrows on them to show kind of how fast these particles are moving and bouncing off the walls of the container when you have a gas. Notice also that the particles of gas are spread far apart. That is a characteristic of a gas. In a liquid and in solid, the particles are very close together. In fact, usually there's not very much difference in the density of a liquid versus a solid. Liquids, the particles are close together, It's just that the particles are free to move past each other. So these particles are still moving, they're just not moving as fast. Okay. They're sliding past each other. They're free to move. The particles are free to move and slide past each other, but they do not, and therefore they don't have a definite shape, but they do still have a definite volume. With a solid, how do we represent a solid? In a solid, the particles are actually still moving. It's just that they're moving very slightly. So sometimes we just kind of do, like in a cartoon, you know how sometimes they do these quotation marks just to show that the particles are just kind of vibrating slightly. Or sometimes people will draw just really small arrows on them, even smaller than we did for the liquid. These particles are not, they're moving even less quickly. And here the particles are not free to move in any direction. They are fixed in place. They're just kind of vibrating in place. So they're moving, but in place. They're not moving around. Because the particles don't move around, this is why our solid has a fixed shape. So this might be some sort of cube of oxygen here. So that's how we can represent solids, liquids, and gases, kind of a model to represent this. And we'll revisit this at various times during the year, especially when we get to the module on gases. But we're also going to be using this module as we talk about energy changes as we move from solids to liquids to gases. Now, I promised that I would show you how to access that textbook of yours. So from your email is the easiest way to do it. When you go to the waffle menu in the top left corner, you may already have Pearson EasyBridge as one of your choices. If it does not appear as one of your app choices, then you need to go to all apps and find it there. However, since I've accessed it before, it's in my favorites here. And when I open up Pearson EasyBridge, because I'm logged into my school email, it automatically logs into Pearson EasyBridge. So this is by far the easiest way to access your textbook. Then you find your class and your textbook. And we're not quite there yet. We have to click Chemistry 2017. And then when you're here, if you just want to read the e-textbook, then you have to click e-text, and you will not have access to the teacher's edition because you are not a teacher. And you have to click several more buttons. It's not as straightforward maybe as it should be. But then it will open up the textbook window here for you. Now this is a large textbook, and flipping through these pages one by one to get to the page that you want would take ages. So go to the menu in the top right corner, go to the table of contents so that you can find the chapter that you want, and chapter 2 looks like it starts at about page 32. So this is a resource for you where you can read about matter and ways to classify matter and things like that in the textbook by reading this if some of what I've told you is kind of news to you. So this is another resource for you to help you look that up. I hope this helps.